When you use the sleep4 function in C++, you might think you're simply pausing the current thread for 1 millisecond. But the underlying operations behind this line of code are far more complex than you imagine. Do you think it's just a pause, waiting for 1 millisecond, and then continuing when the time is up? I'm telling you, that's completely wrong. It's not waiting, it's not idling, not blocking, not a simple delay. This single line of code will directly yank your thread from user mode into kernel mode, trigger a system call, force the kernel scheduler to reselect a thread to execute, and perform a full context switch. A context switch requires saving all register states of the current thread, switching the kernel stack, and possibly even fleshing the TLB. Every step is a deep interaction between hardware and the kernel, far from a simple pause and wait. What exactly is a thread context? You can think of it as the thread's execution snapshot. When a thread is running, the CPU holds a large amount of its execution state. The combination of these elements is its context. Specifically, this includes general purpose registers, the instruction pointer, the stack pointer, flag registers, SIMD, floating point registers, and, if in a debugging state, debug registers. If I forcibly switch the CPU to execute another thread right now without saving this context, what would happen? The result is that when the original thread is woken up again, it will suffer from complete amnesia. It won't know where it was in its execution. The values in its registers will be completely scrambled, and the program will crash. For example, thread A is executing A equals B plus C and has just loaded the value of B into register EX. Before it can load C, it is forcibly switched out, and the value in EAX is not saved. When it wakes up again, the value in EAX may have been overwritten by another thread, leading to a completely correct calculation. Worse, if the RIP pointer is lost, the thread won't know which instruction to execute next, potentially causing the process to exit abnormally. So the so-called context is essentially all the execution state required for a thread to be paused and later resumed, the data needed to save and load a thread state. Today, we'll follow the real path taken within the Linux system from start to finish to see exactly how a context switch happens. Before we begin, we need to be familiar with 3 concepts. First, user mode and kernel mode. The C++ functions we usually write addition, subtraction, multiplication, division, business logic, all run in user mode. User mod has very low privileges, like a regular user who can only do their own tasks. Want to control the CPU, pause a thread, or switch tasks? Don't even think about it. These operations must be completed in kernel mode. Kernel mode is the operating system's administrator mode, possessing the highest privileges, capable of directly manipulating hardware and system resources. There's only one path from user mode to kernel mode, a system call. This is not an ordinary function call. It's a privileged jump at the hardware level, triggering the CPU's interrupt mechanism and directly switching to the kernel's code execution flow. Second, in Linux, a thread is a task. Many people mistakenly believe that processes and threads are 2 different things inside the kernel. But in fact, Linux doesn't have a dedicated thread structure. Whether it's a process or a thread, they look the same inside the kernel. It stores the thread state, priority, scheduling information, kernel stack address, and a complete backup of all registers, the context snapshot we just mentioned, specifically used for saving and restoring during a context switch. Third, and this is the most subversive statement, the CPU has no idea what a thread is. The CPU only recognizes 3 things: the instruction pointer, the stack pointer, and a bunch of general purpose registers, whose register information is loaded into the CPU. That's whose instructions the CPU executes. Thread switching, at its core, is swapping out one set of register data for another. With these concepts in mind, let's return to the sleep4 code from earlier. This is a unified interface provided by the C++ standard library, but it doesn't implement the sleep functionality itself. On Linux, within GCC's libstdc++ library, the underlying implementation of sleep4 ultimately calls a system call nanosleep. This is the core reason why it triggers a transition from user mode to kernel mode. So, what happens the moment a system call is executed? The entire process is a collaboration between hardware and the kernel with no step missing. First, your program places the system call number into the RAX register and then executes the syscall instruction. In that instant, the CPU directly completes 4 actions. It disables interrupts to prevent interruption during the switch, ensuring atomicity, saves the user mode RIP and RSP to record the next user mode instruction to execute, switches the CPU privilege level from ring 3 user mode to ring 0 kernel mode, and based on the system call table, jumps to the kernel's nanosleep handler function sees nanosleep. What does sees nanosleep do next? It mainly does 3 things, with the goal of having the current thread voluntarily give up the CPU, enter sleep, and wake up when the time comes. First, it changes the thread state. It modifies the state field in the current thread's task struct from task running to task interruptible. This means the thread is no longer eligible to be selected by the CPU for execution. Second, it removes the thread from the run queue. It dequeues the thread from the CPU's run queue so that the scheduler will no longer consider it when picking the next thread to execute. Finally, it places the thread into a timer queue. The kernel has a dedicated timer queue for managing tasks that need to be woken up after a certain time. Based on the time specified in sleep 4, the kernel sets a timer for the current thread and places it into this queue. When the timer expires, the kernel automatically changes its state back to task running and re-adds it to the run queue, waiting for the scheduler to select it. At this point, this thread can no longer be executed by the CPU, so the kernel must do one thing: find a new thread to run. This is where the scheduler comes into play. The core entry function of the Linux scheduler is schedule. Its internal logic can be simplified into 3 steps, which are easy to understand. First, get the currently running thread called prev, then call pick next task to select the next thread to run from the run queue called next. If prev and next are not the same, call context switch to perform the switch. Here's the key point. Schedule itself does not save registers or perform the hardware switch. Its only responsibility is selecting the thread, deciding whether to switch and which thread to switch to. How does it select? Linux uses the completely fair scheduler by default. Simply put, each thread has a virtual runtime. The longer a thread has run, the larger its virtual runtime. The scheduler always picks the thread with the smallest virtual runtime to execute next. Under the hood, it uses a red-black tree for management, making scheduling efficiency O log n. The thread is selected. Now, the real magic begins. This part is the absolute core of this video. First, look at context switch. It mainly does 2 things. First, if switching between different processes, prev and next, belong to different processes, it calls switch to switch the address space. This involves changing the CPU's CR3 register to the page table base address of the next process. Why change CR3? Because each process has its own independent virtual address space and corresponding page tables. Changing CR3 means that from now on, the memory accessed by the CPU will be the physical memory corresponding to the virtual addresses of the next process. After changing CR3, the CPU's TLB is automatically flushed because the TLB caches the address mappings of the previous prev process. Now that the page table has been switched, those cached entries are invalid and need to be repopulated with the mappings of the next process. This is precisely why process switches are significantly more expensive than thread switches. Second, it calls switch to. This is the true embodiment of the hardware level switch. It essentially does only 3 things, completing the save and load operations. First, it saves the context of the prev thread. It saves all current registers of the prev thread, including RSP, RIP, general purpose registers, callee saved registers, etc., into the thread struct within prev's task struct. This is like taking a snapshot of prev's current execution state, making it easy to restore when it's woken up later. Second, it switches the kernel stack. Each thread has its own independent kernel stack, used for executing kernel mode code. Switch to function directly changes the CPU's RSP register to the kernel stack pointer of the next thread. The stack is the temporary workspace for thread execution. Once the stack is switched, when the CPU subsequently executes kernel code, it will use the kernel stack of next thread, completely changing the execution environment. Finally, it restores the context of the next thread. It reads all the register information previously stored in next thread struct back into the corresponding CPU registers and finally executes a ret instruction. Where does this ret jump to? It jumps to the place where the next thread was last interrupted and continues execution from there. When the next thread was last switched out, its RIP, the address of the next instruction to execute, was saved in its thread struct. During register restoration, the RIP was also read back into the CPU. The ret instruction automatically jumps to this address, allowing the next thread to seamlessly continue execution from where it left off. So thread switching isn't a pause. It's a wholesale replacement of registers. The CPU is oblivious. It's just swapping one set of data for another. Now, when you revisit concurrency performance, all the issues become crystal clear. Why are locks so slow? A thread fails to acquire a lock, so the kernel changes its state to sleeping, removes it from the run queue, triggering one context switch. When the lock is released, the thread is woken up, its state is changed back to runnable, and it's re-added to the run queue. When the scheduler selects it, another context switch is triggered. So, a single lock contention event results in 2 context switches, 2 rounds of saving and restoring registers, 2 kernel stack switches, and if process switching is involved, 2 TLB flushes. High-frequency lock contention means the CPU spends most of its time switching threads rather than executing business logic. Performance naturally collapses. Why minimize system calls? Every system call requires a round trip from user mode to kernel mode and back, 2 transitions. Essentially, this is 2 simplified context switches, no thread switch needed, just privilege level switching and saving, restoring user and kernel mode registers. The cost of a single system call switch might be only a few microseconds, but the trouble comes with frequent calls. For example, if you spin in a loop frantically calling sleep 4, you are essentially triggering the nanosleep system call repeatedly. Each time performing a user kernel mode switch, performance will instantly collapse. Why are threads lighter than processes? The core reason is that threads share the address space of the same process. When switching threads, there's no need to call switch mn to switch page tables or flush the TLB. Only the switch to register and kernel stack switch is required. Process switching, on the other hand, requires the switch to operations plus the extra step of switching page tables and flushing the TLB. This extra step is extremely expensive, which is why process switching overhead is far greater than thread switching overhead. So C++ is just the surface. The threading library is just the interface. What's really happening is register saving, stack pointer replacement, page table switching, TLB invalidation. This is the true way computers operate. If you want to truly understand concurrency performance, you must understand the context switch. If you found this video helpful, then please don't forget to like, subscribe, and share. See you in the next one.